I'm going to describe an interactive simulation that looks at the effect of changing the tube diameter of a plug flow reactor, observing how this affects the pressure drop, the temperature in the reactor, and the molar flow rate of reactant. And the one variable is that we can change the reactor diameter with the slider, and we can actually change this over a pretty wide range. So this simulation, which is available on the Wolfram site, as indicated here, allows you to change the diameter but keep the total flow rate into the reactor the same by changing the number of reactors in parallel. So if we go to small diameter, we just have more reactors in parallel. So I'm showing you an example. For the smallest diameter, we have 400 equivalent reactors. And this plug flow reactor has heat transfer through the walls. So as we make the diameter smaller, and we've increased the heat transfer area to volume, so we expect to be a smaller temperature increase for this exothermic reaction. It has pressure drop, and as we make the diameter smaller, the pressure drop is going to be larger. So you can see for the smallest diameter, the pressure drops from 6 bar down to less than 2 bar. And then the conversion is shown here. This is the molar flow rate. So the conversion 43%. This is the molar flow rate of reactant that decreases as we react, as we move down the reactor. So what I want to do now is show you how to use this simulation by going to the Wolfram site. And so let's do that now. So here's the interactive simulation on the Wolfram site. So you can see as we change the diameter, let's look at the pressure first. We have significant pressure drop. As the diameter gets bigger, the pressure drop becomes quite small. The temperature, however, as we increase the diameter, becomes significantly higher because we're decreasing the surface area per volume. We have a smaller number of reactors in parallel. And of course, then we're going to get a very high conversion because we're at that high temperature. So as I lower the diameter, I'm affecting the temperature as well as the volumetric flow rate, which affects the residence time. And as I lower the diameter, actually my conversion goes down because I'm affecting the rate constant. So you can use this interactive simulation, give a better understanding of plug flow reactor. Keep in mind the comparison is made for the same molar flow rate into the reactor. And as diameter gets smaller, we just have more reactors, so we're keeping the molar flow rate constant, and we're keeping the cross-sectional area total for the reactors constant.